Welcome back. This is section 10.2, calculus with parametric curves. In the last section, which was 10.1, you learned all about parametrics. You learned what the interesting thing about parametrics is, it allows us to talk about flow, direction. So now we're going to talk about the calculus using calculus with parametric curves. So we need to talk about tangents and how do we find the derivatives. So when we want to find dy dx, we find the derivative of y with respect to t and the derivative of x with respect to t. And then to find the second derivative, we take that dy dx and take the derivative of that and then divide it by that last dx dt that we had. So it sounds confusing, but trust me, it's not that bad. We'll see some examples and see that it really isn't too hard to do. So let me get my pen here. I got black. All right. So here we go. I want to find the dy dx. So I know that dy dt is equal to, that's dy dt, is 1 plus e to the t. Dx dt is equal to e to the t plus t e to the t, right? Because the derivative of t is 1, that gives me the e to the t, and the derivative et is just et times the t. It's a product. So if I want dy dx, I then need dy dt over dx dt. So dy dt was 1 plus e to the t, and dx dt is e to the t plus t e to the t. And that's the solution for this problem. All right. Let's look at another problem. So it's finding the equation of a tangent to the curve at the point corresponding to the given value. So they're telling us what t they want us to look at. So this is saying I want to know what happens at this particular t. So if I want to find the equation of the tangent, that means I need the slope, which means I need the dy dx. So I'm going to find dy dt. The derivative of y is just t squared minus 1. I also need dx dt. And dx dt is equal to 4t. So then we know that dy dx is equal to t squared minus 1 over 4t. So we need the slope, and we're told that t is equal to 3. So my slope is what happens at t equals 3. So 3 squared minus 1 over 3 times 4, or we end up with 2/3. So there's my slope. If I have a slope, and I want to find the equation of a line, I can use point slope, which is y minus y sub 1 times x minus x sub 1. So first of all, I need to know what happens at a particular, I need to find the points, sorry. So I know that x is equal to what? When 3 times 3 squared plus 1. That's going to give me the x value. And that's going to tell me it's 19. And y is equal to 1/3 times 3 cubed minus 3. And that turns out to be 6. So the point, you need a point. Here's the point I'm going to look at, and here's the slope I want. So now I have everything I need to find the equation of the line. Y minus its known y value of 6 is equal to the slope of 2/3 times x minus the x value, and the x value is 19, which we found just a few seconds ago. I can run through all this. You can do this on your own to verify the answer, but the equation line is 2/3 x minus 20 over 3. You don't need to watch me actually work out that equation. You can do that algebra yourself, right? And anytime I'm asking for the equation of the line, I want it equals y equals mx plus b, slope-intercept form. Alrighty. So now I want to find the equation of the tangent to the curve at the given point by two methods. First, I want to do it without eliminating the parameter, and then by first eliminating the parameter. So there's more than one way to do this. So let's see. What is dy dt? Dy dt. Well, dy dt is y is equal to secant theta. So the derivative of secant theta is secant theta tangent theta. Dx dt, x is equal to tangent theta. The derivative of tangent theta is secant squared theta. So dy dx is equal to secant theta tangent theta all over secant squared theta. And that reduces to tangent theta over secant theta. All right. And then if I look at that, I could rearrange that and figure what that turns out to be. Well, that's a sine theta over cosine theta over 1 over cosine theta. That just turns out to be sine theta. That's my dy dx. All right. So here's my dy dx. So let's see, what else do we have? So hold on for one quick sec. Sorry, I had to get a drink of water real quick. So let's look at something. If tangent theta gives me my x is 1. So that means that's a 1 and a 1. If secant theta gives me a y value, that's square root of 2. That's square root of 2 over 1. Well, what triangle is that? Theta has to be equal to pi over 4, doesn't it? Happens to be that. So my theta is pi over 4. All right? Because arctangent of 1 is pi over 4. And arcsecant of square root of 2 is pi over 4. I'm just verifying that. So we find out the equation line. So we're going to find the equation line in a minute. I'm going to start the second method, which was elimination. I'm going to change colors. So how do I eliminate? Well, I have a fact that I know tangent squared theta plus 1 equals secant squared theta. Going back up here, right? I have x's and y's. So I get an x squared plus 1 is equal to y squared. So then what do we have? We have, I can take the derivative of both sides, right? So if I take the derivative of both sides, 2x, because I want to find the slope. So 2x is equal to 2y dy dx. And it's 2y times that, so I can divide everything through. So I end up with x over y is equal to my dy dx. And we know what x and y are, so x is a 1 and y is square root of 2. So my slope is 1 over square root of 2, right? And let's go back in here. We said slope was this. Well, what is, hold on, let me change this. Sine of theta. Well, sine of theta is sine of pi over 4. Well, that's just 1 over square root of 2. So I'm getting the same answer, same slope. So now going back to the equation of my line, I need a y minus my known y. This is equal to m times x minus my known x value. I know that it's y minus, well, my y value, going back up here, my y value is the square root of 2. See, right there, square root of 2. Is equal to my slope of 1 over square root of 2 times x minus my known x value. My known x value is a 1. All right, so I end up with a y is equal to x over square root of 2 minus 1 over square root of 2 plus a square root of 2. And I can finish that off. X over square root of 2 minus 1 plus square root of 2 over square root of 2. Oops. Minus 1 minus 2 over square root of 2. All right. Oh, they left it like that. Huh. Interesting. Well, let's just talk about how I was going to do this problem. We'll finish it off real quick. 1 over square root of 2. I want to make this 2 over square root of 2. All right? Because I'm going to rationalize this by multiplying by square root of 2 over square root of 2. So I get y is equal to x over square root of 2 minus 1 plus 2, or 1 over square root of 2. All right, so now it says there's a different problem. It says, I want to find dy dx in the second derivative. So this one's going to be a little messier. It's got a lot more parts to it. And we want to find out for which values this is curved. The curve is concave up. So when we're looking at the second derivative, we want the second derivative to be greater than 0. All right, so let's start off slowly. dy dx. Well, dy dx, oh, not d, well, dy dt. Let's go dy dt. dy dt, here's my y. It's just 2t. dx dt, well, there's my x. 3t squared minus 12. So now we have a dy dx is equal to 2t over 3t squared minus 12. But that only gives me my first derivative. I then need to take dy dx and to take that to get my second derivative. Well, here comes the mess. I take it's a quotient, so I take the denominator and square it, right? Then I take the top, take the derivative of the top, which is t, times the bottom, 3t squared minus 12. Subtract from it the derivative of the bottom, which is 6t, times the top, 2t. And all that, right, because this is supposed to have a dx. What was dx? 3t squared minus 12. So I still need this, because we said dy dx is equal to dy dx dx. So, yeah, anyway, so it's the second derivative. So let's clean up this mess here. Got a mess here to clean up. So in the numerator, I distribute the t. I got a 3t cubed minus 12t minus 12t all over 3t squared minus 12 quantity squared all over 3t minus 12. Well, that's nice because if I'm paying attention, this will cancel out one of those. So that simplifies to 3t cubed minus 24t all over 3t squared minus 12. All right. Did I copy something? Oh, yes, I did. Wow. I cannot read my own handwriting, apparently. So this is a mistake, and I'm going to fix all of this. I apologize. Unfortunately, I cannot edit this. So let's go back, if I can only read my handwriting. This was supposed to be 2, right? The derivative of the top is just 2, not t. I don't know why I wrote that. So it's 2 times 3t squared minus 12 minus 6t, 2t over, or everything else is right. So now we have that correct. Now let's distribute 6t squared minus 24 minus 12t squared all over. And as we already saw, we could simplify by canceling one of these with that. And there it is. I can combine my like terms. I get a minus 6t squared minus 24 all over 3t minus 12. All right. So I could simplify that a little bit more. I could take a minus 6 out, give me t squared plus 4 all over 3 times t minus 4. That really doesn't help. That's a t squared. That doesn't help me, but what it does do is allows me to see, well, I can take out that minus 3 t squared plus 4. The denominator factors to this, correct? And since that factors, we're looking for critical points. What makes the numerator 0? Well, nothing's going to make this numerator 0. But this is important. So I'm going to look at a number line. -2 and 2. Those are the points I care about. And I'm going to see what's going to happen. I'm going to use test points. I'm going to use test points. I'm going to say, all right, what happens at 3 0, and negative 3. When I put a negative 3 into this, the top is always going to be negative. That's not going to change. And the bottom, right, so looking at this, I have minus 3 t squared plus 4. I'm going to just leave this as t squared minus 4. This is always going to be, the numerator will always be negative. I can't control that, no matter what t I put in, because t squared plus 4, t squared is going to be positive, plus 4 is going to be positive. Multiplied by a negative 3, it's always positive. In the denominator, when I put a 3 in, negative 3 gets squared, it's positive, it's 9. 9 minus 4 is positive 5. So when I check this out, the numerator is negative, the denominator is positive, so the result's positive. When I put 3 in, I'm going to get the exact same result. But when I put 0 in, the numerator is negative, the denominator is negative, and negative divided by negative is positive. So in this interval here is where it's concaved up. So it's concaved up in the interval from negative 2 to 2. I believe that's all they wanted, right? So we want to find, so it's concaved up, like I said. All right. Let's go on to the next page. I want to find the points on the horizontal curve, or find the points on the curve where the tangent is horizontal. So I care about when it's horizontal, and I care when it's vertical. So before I get further, when m is equal to 0, horizontal. When m equals undefined, vertical. So we got to find the slope, which means tangent. Which means derivative. So dy dt, the derivative of the y, is 6t squared plus 6t, and then dx dt is 6t squared plus 6t minus 12. Here's my x, here's my y. So dy dx, I'm going to just build them together. So 6t times t plus 1 all over 6 times, I'm going to just factor it, t plus 2, t minus 1. These 6's cancel. T times, that's a t, times t plus 1 all over t plus 2 times t minus 1. Alrighty. So now, this is my slope, and I want to find out when it's horizontal. Well, again, horizontal means I care about when t times t plus 1 equals 0. That's at t equals 0 and negative 1. And I want to know when it's vertical. That happens when the denominator equals 0. And that happens at t equals negative 2 and positive 1. So now if I want to know the exact points, I would take those t's and put them back into here. I will leave that up to you to do on your own, just to save some time, because this is a very long section. And these are your answers. All right. And I get the horizontal by taking this, so into x is equal to 2t cubed plus 3t squared minus 12t. Y is equal to 2t cubed plus 3t squared plus 1. That's going to get me that. And then to find the vertical, again, I'm going to sub into that same equation. That gives me the points where the tangents are vertical. So it's important to be able to do that. But I think that's a simple enough concept for you to do on your own. So now we're going to look at this, and we want to find the same sort of thing. So I'm going to rush through this a little. Dy dx is equal to dy dx is equal to 2 cosine 2 theta, right? Not dy dx, dy dt. Dx dt is equal to minus 2 sine theta. So dy dx, all I'm doing is building it up. 2 cosine 2 theta all over minus 2 sine theta. Well, these 2's cancel out. You got a minus cosine 2 theta all over sine theta. It doesn't matter where I put that negative. I'm just going to write this a little clearer. Cosine 2 theta sine theta. Again, it doesn't matter where I put that. All right. So now I'm going to simplify this. I'm going to put the negative out front. Cosine 2 theta can be rewritten. And that, again, is on your sheet that I will provide on the test. That's cosine squared theta minus a sine squared theta. And then the bottom's just sine theta. But now I have everything in thetas. It would be a lot easier to evaluate this. Horizontal, because now I have my slope. Horizontal happens when cosine squared theta minus sine squared theta is equal to 0, or cosine squared theta is equal to sine squared theta. So where does that happen? If I look on a unit circle, it happens at these 4 points, right? Because they're getting squared. They're both positive here at pi over 4. One's positive, one's negative, but when I square it, they're the same sign. One's positive, one's negative. They're both negative here at 5 pi over 4. But that's okay, because when I square it, they're going to be the same anyway. And at 7 pi over 4, one's positive, one's negative, but I'm squaring them. So my theta is pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And now that I know that, I can go put that back into the original. So I'm going to sub theta into x is equal to 2 cosine theta, y is equal to sine 2 theta. And that would tell me the points. Again, I'm not concerned about the points. You would want to do this, and I'm going to show you the answer in a minute. Where is it vertical? Vertical when minus sine theta equals 0. Well, sine theta equals 0 at 0 pi. We're going to say 2 pi if we want. And again, sub theta into x equals 2 cosine theta, y equals sine 2 theta. And that will give you the points. And here are the points that you should get. All right, those are all the points. Again, that's a nice exercise for you to do on your own. I'm more concerned that we could find the derivatives, especially because this can be a very long video with all the things I need to cover. We're about maybe a third to a half away. This one may be the first one that goes to an hour. All right, at what point on the curve x equals t cubed plus 4t, y equals 6t squared is the tangent parallel to the line with this equation? So first I'm going to look at this line. Say dy dt is equal to 12, and dx dt is equal to minus 7, or dy dx is equal to 12 over negative 7. Now I'm going to look at that. I'm going to change the color of my ink so I know I'm taking a different one. Dy dt is 3t squared plus 4. Whoops, I just did dx dt. Dy dt is 12t. Dx dt is equal to 3t squared plus 4, or dy dx is equal to 12t over 3t squared plus 4. And again, I just want to highlight that so we're on the same page. So now I have those two, and I want to know when they're equal to each other, right? That was the question. It said, at what point on the curves x equals t cubed plus 4t, y equals 6t squared is the tangent parallel. So now I have my tangents. I want to know when they're equal to each other. So I care to know when is 12t over 3t squared plus 4 equal So minus 12 over 7. And I don't know why there's two negative symbols here. So all I have to do is cross multiply. All right. I get 84t is equal to minus 36t squared minus 48. I can bring everything to one side. So I end up with 36t squared plus 48. Oops. It is plus 48, but I like to keep things in order. Plus 84t plus 48 equals 0. I could factor out 12 from everything. So that gives me 3t squared plus 7t plus 4 equals 0. And then I could factor that trinomial, 3t plus 4t plus 1 equals 0. So t equals 4/3 negative and negative 1. If I want to know the points, sub these t's into the original equation. X equals t cubed plus 4t. Y is equal to 6t squared. And I will show you those points right here. That way you can confirm your own work. But again, for the sake of saving time, this video will be long. I'm just going to give you the answer. So now we're going to look at this. I want to talk about the area between curves and the x-axis. Hold on for a second. Sorry. So again, we want to find the area between the curves. I need to have x equals ft, y is equal to gt, dx is the derivative of ft dt. So we said the area of this function is from t sub 0 of gt times the derivative of ft dt. So and then now doing the y curve, we have everything in terms of that. So it's t sub 0 to t sub 1, t sub 0 to t sub 1. And now we're going to look at the function f of t times the derivative y. So g prime t of dt. So that's how we're going to find these problems. So we're going to look at the first one. It says determine the area bounded by the curve and the y-axis. So we care about the y-axis and the area of the curve, which is going to turn out to be that side. Just trust me, I know what I'm talking about. So I got let's see, f of t is equal to this, and g of t is equal to that. So I want to integrate from a t sub 0 to a t sub 1 of f of t g prime of t. Well, what is g prime of t? G prime of t says take t and take the derivative of that, which is minus sine t. F of t, as we already said, was sine of t. So what do we have? We're going from 0 to 1 pi, 0 to pi, and it's the opposite of sine t times sine t dt. I'm going to stop for a second, and you notice I put 0 to pi. Let's look at this function real quick. It's important, so clear this window, zoom square is 5. Let it run through real quick. We're only going from 0, sorry, I started this 0 to pi, window from 0 to pi, and then our function, like I said, it's sine of t for x, cosine of t is y. Now watch how the function is drawn. It's only that half. So this is where it gets interesting. This was t of 0. That's equal to 0. And this was t sub 1, which was equal to pi. We're drawing our strips this way, correct? It should be the top subtract the bottom. So what's the lower unit? T sub 1. So in this case, it would have been pi to 0 because we're in the y direction. So you have to pay attention to that sometimes, right? I know it says going from 0 to pi, but when we look at this and see how everything's oriented, we're going to have to do it this direction. If we did from pi to 0, or from 0 to pi instead, we'd get the opposite of what we want. We'd get a negative. And then you would just fix that problem. But to save ourselves some time, we're going to fix it right now. Pi to 0 sine squared t dt. So I need to take the derivative. I don't know how to take the derivative of that, but we had some tricks that we learned in chapter 7. We rewrite that as 1/2 times 1 minus cosine 2 theta d theta. I'll bring that 1/2 out. Pi to 0, 1 minus cosine 2 theta d theta. Take the derivative, take the integration of that. That's theta minus 1/2 sine 2 theta, and evaluate it from pi to 0. And when I do that, I get a minus 1/2. Put 0 in. I get 0 minus 0 minus, put pi in, pi minus, that turns out to be 0. So I end up with a minus 1/2 times the minus pi, which is just pi over 2 positive. So if we would have done it the other way from 0 to pi instead of pi to 0, we would end up with a minus pi over 2. And that doesn't make sense when we're talking about the area, right? The area bounded by the curve is going to be positive. All right, so this time we want to set up but do not evaluate the integral that would determine the area bounded by this curve. And y equals 2.5. So this is what it looks like. Hold on for a second. This is y equals, oops, this is y equals 2.5. There's a point here and here. In black is this curve. I could show you on your calculator, but just trust me, that's what the curve looks like. I'm just trying to, again, save some time. I could put in my calculator. You can see that actually. Give me a second. I will show you. Okay, so I went in here and I looked at the function just to prove it to you. This is x is t minus 1 over t and y is t plus 1 over 2t. When I draw it, here it is. The only thing we don't have is the 2.5. Y is equal to 2.5. So here's one. Here's about 2.5. I'm going to fix it a little better. So now we can see it's exactly what I drew. All right, so I just wanted to show you so you see what I'm looking for. All righty, so now we have all this, and we need to figure out when these two things are equal to each other. So we will care about when this y is equal to 2.5 because they're both y's. Right, so we care about that. We care about when does this y equal that y. So we have t plus 1 over t is equal to 2.5. I can multiply everything through by t. I get t squared plus 1, so 2.5 t. Move everything to one side. T squared minus 2.5 t equals 1 plus 1 equals 0. Plus 1 equals 0. I can multiply everything through by 10, so I get 10t squared minus 25t plus 10 equals 0. I can factor out a 5. 2t squared minus 5t plus 2 equals 0. And then I can factor that. And that factors to 2t minus 1 times 2t, whoops, not 2t, times t minus 2 equals 0. So t has to happen. T is at 1/2 and 2. Those are the two t's. So it's a setup, but do not evaluate the integral that would determine. So now we know My limits of integration are from 1/2 to 2. And then I have to set up my equation. So it's 2.5 minus y times my derivative f prime of t. All right. So the question is, why is it 2.5 minus uh, 2.5 minus y? Well, this is y, right? So I need my y value. That's according to what we were doing. So so I need to have that, right? So I have to separate them by subtracting them one from the other. And now let's put it in dt. So I have 1/2 to 2. 2.5. So it's 2.5 subtract. Well, what was y? Y was t plus 1t plus 1 over t times the derivative of f of t. So that gives me 1, right? The derivative of this, that's f of t. That's my g of t. The derivative of f of t is 1 plus 1 over t squared, right? Because the derivative t is 1, and the derivative 1 over t is a minus. There's a minus in front, making a plus. dt. And that's all they want us to do. They don't want us to actually evaluate this. They just want us to set up and do not evaluate. So there it is. They went a little further. They distribute. All right, if I distributed, I get exactly what they have. 1/2 to 2.5 minus t minus 1 over t times 1 plus 1 over t squared. And that's all I want you to do. I don't want you to go any further. I don't need you to distribute that and what have you. So now let's look arc length. We did this before in section 8.1 or 8.2, whichever one we did arc length for. And now we're going to say it's the same thing for parametrics. Use that same concept, but instead now I'm going to have dt's. So this is the formula we're going to use. So here we go. I want a dy dt. Well, that means I have to take the derivative. I think it's r cosine t. The x dt. Take the derivative of the x. Gives me r sine t with a negative. So now I'm going to go from a to b of dx dt squared plus dy dt squared, take the square root of that, dt. So we have our dx dt, we have our dy dt. I'm going to go from 0 to 2 pi, so I'm going to go from 0 to 2 pi. Dx dt squared gives me a positive r squared sine squared t. That's my dx dt squared. Plus my dy dt. Well, dy dt is r cosine t. When I square that, I get r squared cosine squared t. Let's take the square root of that. From 0 to 2 pi. Well, they both have an r squared, so I'm going to factor out the r squared. Leaving behind sine squared t plus cosine squared t dt. That r squared can come out. It's r. Remember that r is like a constant. I have a sine squared t plus a cosine squared t. Well, I know what that is. That's just 1, isn't it? And the square root of 1 is just 1. Now I got to integrate. And it with a t from 0 to 2 pi. So r is equal r times 2 pi minus 0, or 2 pi r. So determine the circumference of a circle, right? Determine the circumference of a circle. Wow, that's a big surprise. The circumference of a circle, 2 pi r. We already knew that formula. So It's just confirming that that's correct. That's why we use that formula there. All right, set up but do not evaluate an integral that represents the length of the curve. So again, I need a dx dt, and that's just 1. Derivative 1 is 1. Derivative e to the t is e to the t. I need a dy dt. Derivative t squared is 2t. So I want dy dx. My dy dt is 2t. My dx dt is et. Oops, I don't need that. I'm making up stuff now. All right, so I'm integrating, sorry, from an a to a b, or t sub 0 to t sub 1, t sub 1, of dy dx dt squared plus dy dt squared, take the square root, dt. So my a to b is a negative 3 to 3. My dx dt is e to the t, so e to the t squared, that's easy, plus 2t squared, take the square root, dt. We'll clean this up nicely. I'm going to go from negative 3 to 3. Let's see if I can write this a little better. Negative 3 to 3. E to the t squared is e to the 2t, plus 2t squared is just 4t squared. I'm going to take the square root of the whole thing, dt. And that's the same answer. So here we go. So that, again, we weren't evaluating. We just wanted to do this. There may be problems on the test that I ask you to go this far, and this is about as far as you can go. You can't do any more. When I'm asking you to set up but do not evaluate, I want you to do as many steps as possible. Simplify it as much as possible, right? I don't want you to actually solve it. I want you to get as simple as possible. So now it says graph the curve and find its length. We're not going to graph the curve. I mean, you can do that on your own just by putting in your calculator to see what the curve looks like. So let's find our parts. If I want to find the length, that means I have a t sub 0, t sub 1, dx dt squared plus a dy dt squared. Take the square root of the whole thing, dt. So dx dt, that is a big mess, isn't it? So the derivative e to the t is e to the t times cosine of t, times the derivative cosine t minus sine t, e to the t. We'll rewrite that as e to the t times cosine t minus e to the t sine t. Just make it a little cleaner. dy dt, well, it's the same sort of process. Derivative e to the t is e to the t sine t. Derivative sine t is plus sine t times e to the t. And again, we'll clean it up to put the e to the t's in front. Just makes it a little easier to see what we have. So, e to the t, wow. I'd like to say no one corrected me, but there's nobody here to correct me. So let's do the derivative of dy dt. You're all probably going, what the heck's going on? That makes no sense. So let's fix that. So derivative e to the t is e to the t times sine t. Derivative sine t is cosine t. I swear I thought that, and I just didn't write it. E to the t. This looks a lot better now. Just rewriting it so the e to the t's are in front. Alrighty. So now we have our dy dt and our dx dt, but we need a dx dt squared. So that means I need to take this and square it. That's going to be this mess over here when I'm all done. So e to the t cosine t squared gives me, right? It gives me e to the 2t cosine squared t minus, because there's a minus, 2 e to the t sine t cosine t plus e to the 2t sine squared t. So now we have that. Next, we have to figure out what that is squared. So we need dy dt squared. Well, I'm going to e to the t sine t squared is e to the 2t sine squared t. Then I have 2 times e to the t sine t times e to the t cosine t. So I end up with 2 e to the t sine t cosine t plus uh, e to the 2t cosine squared t. All right, hold on for a quick second. All right, I'm back. Sorry about that. And let's see. There is a small problem. This times this, not that's going to make a difference, but that's what it should have been. So we have that all done. Now I want to integrate from 0 to pi. And I need my dx dt. Oh, I didn't change that. I didn't highlight this blue like I wanted to. That's an e to the 2t cosine squared t minus 2e to the 2t sine t cosine t plus e to the 2t sine squared t. I'm going to add to that dy dt, which is e to the 2t sine squared t plus 2 e to the t sine t cosine t plus e to the 2t cosine squared t. I'm going to take the square root of this entire thing. And hopefully I notice that I had to break it up in 2 lines because no way it's going to fit. This part will cancel out with this. So now I'm going to rewrite this 0 to pi all in one line, e to the 2t cosine squared t plus an e to the 2t sine squared t plus an e to the 2t sine squared t plus e to the 2t cosine squared t, all under this big d to the t. So hold on for a second. Yep, we're good. So what do I have? Let's gather up some terms. I have this and this, which gives me 2e to the 2t cosine squared t plus this and this, 2e to the 2t sine squared t dt. I could factor out, they both have a common factor, 0 to pi of 2e to the 2t times cosine squared t plus sine squared t dt. Again, paying attention, this part goes to 1. So I'm going to 0 to pi of 2e to the 2t dt. I could clean that up some. So I could take out the square root of 2 from 0 to pi. And then e to the 2t, take the square root of that part. That's just e to the t. When I well, I'm going to take the integration of that. That's just e to the t from 0 to pi, square root of 2 of e to the pi minus e to the 0. Well, e to the 0 is 1, so I'm going to square root of 2 times e to the pi minus 1. And that's what it should say as the answer here. These get long and it's easy to get lost. When working on these, you have to be very careful that you don't lose signs and you don't lose parts of this. These things get very messy very quickly. So let's see how much more do we have left. We have just 4 more slides and then we'll be done. So surface area. So we did area. Now we're going to do surface area. And again, these are all the formulas I need to know. So you found arc length, which is dx dt squared plus dy dt squared all into the square root. Now we're going to have surface area. So if I'm going around the x-axis, I want a y. If I'm going around the y-axis, I want an x. Everything else, this didn't change, that didn't change from the previous slide, because that's still 2 pi, and that's still dx squared dt squared. So all you're really got to clue in on, I got a y because it's an x. I have an x because it's a y-axis. So if I can keep that straight, it'll make my life a lot easier. So determine the surface area of the sphere using a parametric representation. So I'm looking to be a 2, whoops. I'm looking for a 2 pi from A to B. And, whoops. Determine, so if I'm going to, so, well, just give me a second. dx dt squared plus dy dt squared dt. 0 to pi. That means I'm going to go surface area around here with respect to x. Therefore, y is what I need. That's how I know what I'm using, right? That's what it says, 2 pi with respect to x, use a y. So I'm going to 2 pi. I'm going from 0 to pi of y. Well, the one thing I haven't found yet, what is dx dt? Well, dx dt is minus r sine squared, minus r sine t. dy dt is equal to r cosine t. So now I need to square them. I need a minus r sine t, and I want to square it, and add to that r cosine t squared. Take the square root of that whole thing. That's nice because when I square it, I get a 2 pi, 0 to pi, y. This gives me r squared because something negative squared is just positive. Sine squared t plus r squared cosine squared t. These are all dt's. They both have an r squared I can factor out. It's a constant. R squared, square root of that is r, so I'm going to just bring it out front. Y. I end up with a sine squared t plus a cosine squared t dt. Well, this whole thing's 1, so I end up with a 2 pi r from 0 to pi of dt, y dt. Right, because the square root of 1 is just 1. I'm going to integrate 2 pi r y squared over 2 from 0 to pi. But before I do that, this 2 and that 2 will cancel. Pi r times y squared from 0 to pi. So I end up pi r times pi squared minus 0, or pi cubed r. Why is I think I lost a number somewhere? Hold on, let me look at something. Okay, apparently I am very tired. It's been a long day of recording. This problem was done a little bit wrong. What did I do wrong? I'm going to leave this here to show you what I did wrong, but I'm going to tell you this. What is y? I'm not doing y. How can I do y? Everything's in terms of t. Yay. So I'm going to just delete this from here. Let's delete it from this point on. Instead of y, we don't put y. Everything's in terms of t. How am I taking the derivative? It doesn't even make sense. So I apologize. I'm getting very tired, and apparently I'm getting a little punchy here. So I still want a 2 pi. We know that y is equal to r sine t. So now we can do the problem right. Instead of y, it's r sine t. Everything's in the same variable, right? We got r squared sine squared t plus r squared cosine squared t dt. Now let's see if we can get this correct. I got 2 pi. This r comes out. I get r squared because I multiplied that by r. 0 to pi. 0 to pi. I assign t of a sine squared t plus a cosine squared t. Again, I apologize for that mistake. So I have 2 pi r squared from 0 to pi of sine t. This part here goes to 1. Now, let's integrate this. So I have a 2 pi r squared times a minus cosine t from 0 to pi. Let's write this so that people could read this later. Minus cosine t, and I'm evaluating from 0 to pi. 2 pi r squared minus cosine of pi minus a minus cosine of 0. Well, that gives me 2 pi r squared. Cosine of pi is -1 with a minus in front because of positive 1. Subtract. Cosine of 0 is 1. There's a minus in front, so it's -1 plus 1. Or 4 pi r squared. That, my friends, is the correct answer. And again, I apologize for making a mistake. We have one more. This has been the longest one I've had to do. I'm going to watch every step I take so I don't make any mistakes. Let's end with a good problem. Set up but do not evaluate. So it's a little harder to mess up because I don't have to evaluate. An integral that represents the area of the surface obtained by rotating the given curve about the y-axis. So I'm going about the y-axis, right? So let's set that up. That means I want a 2 pi. I want a 2 pi from A to B, but not y. This time I want x, which, by the way, we're going to remember to put sine squared t of a dx dt quantity squared plus a dy dt quantity squared dt. So that's everything that we're going to be looking for. So let's find out what is dx dt. Dx dt is 2 sine t cosine t. Dy dt is equal to 3 cosine 3t. All right. So we have to square these. So dx dt squared is equal to 4 sine squared t cosine squared t. And dy dt squared is equal to 9 cosine squared 3t. So we have our parts. So now we're going to substitute. I'm integrating from 0 to pi over 3. We said we want x, right? We wanted the x here. X is this. So we're going to put sine squared t. There's my x. I'm multiplying that. I need my dx dt squared. 4 sine squared t cosine squared t plus my dy dt squared 9 cosine squared t. Take the square root of the entire thing. Again, this and this. Whoops, why did that not change? This and this make up this part of the equation. And don't forget to write dt. And that, my friends, is the problem. Oh, I forgot 2 pi. Oh, 2 pi. 2 pi sine squared t. Take the square root of, I don't know why they have that written that way, but they're wrong. It's missing the 4 out front. Oh, sorry. Well, that's a 9. Oh, they rewrote. Oh, I see what they did. Let's see. Let's talk about what they did. Because they rewrote that. Let's talk. This is really quick. This part here. Remember 2 sine squared t. I'm sorry. 2 sine t cosine p is equal to sine 2t. So if I double everything, square that, that's where they get the sine squared 2t. That's where this comes from. It's the same thing, just a different form. So that is all I have for today. That gets us through 10.2. Sorry, this one's a long video, but it's a long section. Thank you very much, and I look forward to seeing you in class.